This is section 11.3 on simplifying radicals. Now that we have the basics of radicals down, we're going to work a little bit more with them. So make sure you have your power chart handy. Eventually you'll really get to know your squares and your cubes, but it's handy to have them here just in case. And also sometimes you'll have fourth roots to work with, not so much fifth and sixth roots. So we have what we call the product rule for radicals, which we've kind of already seen, but I wanted to make it explicit. If you have a particular root of one value times a particular root of another value, these roots have to be the same, then you can combine those values under the radical with multiplication. Or if they're already combined, you can separate them out into two separate roots, which we tend to use to help us work some more challenging problems. We'll break it into two pieces to help us out. So this is just a demonstration of how that rule works. So if we have the square root of 9 times the square root of 4, I want to show you that it's also the square root of 36. We know the square root of 9 is 3. We know the square root of 4 is 2. And we know the square root of 36 is 6. And you can see 3 times 2 is also 6. So that's just demonstrating that the rule is valid. Just a short demonstration. But let's use that rule to help us simplify different expressions. So if I have the square root of 5 times the square root of 2, I can put those together since they're both square roots and make it the square root of 10. If I have the cubed root of 7 times the cubed root of 9, because they're both cube roots, I can combine them together and make it the cubed root of 63. If I have the square root of 5x times the square root of 3y, again because they're the same root, they're both square roots, I can combine that and make that 15xy, or separate it back apart if I need to. And finally, if I have the fourth root of 5x to the third times the fourth root of 4, because they're both fourth roots, that can combine to become the fourth root of 20x to the third. So that's just practicing the product rule. You'll see it come into play every now and then to either separate two pieces out or to put two things together to make it easier to look at. We also have what we call the quotient rule for radicals. And we've also seen this before. I just wanted to make it explicit. It just introduces it in this section even though we've kind of already seen it. I have a root of one number divided by the same root of another number. I can put them together under the same root. What we saw in the previous section is separating it out into two separate roots. So an equal sign works either direction. So I can take two separate things and put them together if that will help me solve it, or take something that's together and separate it out if that will help me solve it. Either way. So a quick demonstration of that. If I have the square root of 64 divided by the square root of 16, I want to show you that that's the same thing as the whole square root of 64 divided by 16. So on the left, the square root of 64 is 8, the square root of 16 is 4, and 8 divided by 4 is 2. On the right, if I do 64 divided by 16, that gives me 4, and the square root of 4 is also 2. So again, just demonstrating how that rule works. So let's simplify these using the quotient rule. So we've seen this one before. If I have the square root of 9 over the square root of 64, I can separate that into the square root of 9 divided by the square root of 64 and get 3 over 8. So separating it into two pieces helps me solve it. Same thing here. I can separate this into the square root of x over the square root of 16y to the fourth. Square root of x, there's nothing I can do with that, but the bottom, the square root of 16, that's a perfect square, and y to the fourth divides nicely with 2, so I can create a little bit simpler of a problem. Radical x will stay on top, square root of 16 is 4, square root of y to the fourth is y squared. Notice the denominator no longer has a radical. Same idea with this one. We have the square root of 2 over the square root of 8 x to the 15th. Trying to think. With that one, I'm going to change this here. It's actually better to do it a different way. So the 2 and the 8, and you just have to look at what you have. So sometimes you'll do something like I just did and think, well, that didn't really help anything. So there's other things you can try. Here, if you notice, the 2 and the 8 will reduce, and we can make this the square root of 1/4 x to the 15th. Now we can separate it and actually get somewhere. So the square root of 1 is 1, the square root of 4 is 2, and I'm going to leave the square root of x to the 15th under the radical for now. We'll deal more with how to work with that here in just a few minutes, but I'm just going to leave it just like that for now. And last but not least, here, I'm going to separate that to the square root of x to the 14th over the square root of 25y to the 10th. The square root of x to the 14th is x to the 7th. Square root of 25 is 5. Square root of y to the 10th is y to the 5th. So the quotient rule comes in handy. You can kind of break things apart, separate them out, reduce if needed. Kind of helps you get down to a more simplified answer. This next part of the notes is extremely important for college algebra. It's something you'll see again and again, and the instructor that you have most likely will expect you to already know this concept. So you want to get very good at it. We are going to see it several times throughout the rest of the course, but it's something that is just a very important skill when you get to college algebra. This textbook calls it simplifying radicals. I tend to call it breaking down radicals. It's also referred to as reducing radicals. So it's all the same idea, simplifying, breaking down, or reducing radicals. In order to break down radicals, you must think of or find the biggest perfect square or cube that divides nicely, or which means it's a factor, of the given value under the radical. So we're going to rely very heavily on our power chart for this. We're trying to think of the biggest perfect square or the biggest perfect cube that divides nicely or makes it a factor of the number under the radical. Very important to either know these numbers by heart or have this handy to help you with this concept. So it's best to just kind of jump into these. There are several different ways to teach this, so I'm going to show you the way that works for most of my students. If that's not clicking, the tutoring centers at any of the campuses can help, or you can come see me and see some different ways to look at it. But hopefully this is the most efficient method, and it works for most students. So we have the square root of 50, which is not a perfect square. We don't want big ugly decimals because that doesn't help us. So what we're going to do is look on our list of perfect squares, and we're going to find the biggest one on this list that divides nicely by 50. So if we get on the list, 1 divides by 50, but it's not a big number. 4 does not divide by 50. 9, no. 16, no. 25 does divide by 50. 36 does not. 49 does not. And after that, it's just too big. So if you're not too confident with your multiplication and division skills, you can always let your calculator help you out. The 50 divides nicely by 25. 25 and 2 are factors of 50. So you have to find the biggest perfect square that divides nicely by that value. So 25 is your biggest perfect square. From there, we're going to use the product rule that we just learned, knowing that I can break this apart into 2 pieces, that the square root of 25 times the square root of 2 is equivalent to the square root of 50. Well, we know the square root of 25 is 5, and the square root of 2, we can just leave the square root of 2 because it's a big ugly decimal. It's not a perfect square. So in your perfect square, we take the root. Your non-perfect factor that goes with it, we just leave it in the radical. And so the square root of 50 is that big ugly decimal, and that's equivalent to 5 times the square root of 2, not 29, of 2. So all we're doing is rewriting the radical 50 into a broken down or simplified or reduced, kind of like reducing fractions. We're doing the same thing. We get an equivalent value that's written in a more simplified form. And you'll see why this comes in handy in the following sections. Let's try it again with 20. So 20 is not a perfect square, which means I need to think of the biggest perfect square in my list that divides nicely into 20. And from this list, 4 is your biggest perfect square that divides nicely into 20. And that would be a factor with 5. 4 times 5 is 20. So again, we're looking for that biggest perfect square. Square root of 4 is 2, and the square root of 5 stays the square root of 5. So the square root of 20 can be broken down into 2 times the square root of 5. With 48, I need to look at my list, think of the biggest perfect square. I believe it is 16. So 48 divides by 4, but that's not the biggest perfect square. 48 also divides by 16. You want to think of the biggest perfect square you can so that whatever factor it goes with is as small as possible. So 12 still has some factors in it, and 3 does not. So you want to get as small as you can with the other number, which means you want the biggest perfect square. I'm sorry, I said that confusing. Just focus on your biggest perfect square. Some students tell me that they'll go up the list backwards so that they don't get a small one and move on. So start from the bottom up and start from the biggest number so that when you get to 16 you don't even have to worry about 4 because 16 is going to work for you. I hope that wasn't too terribly confusing. Alright, so 16 and 3. 16 again is your biggest perfect square. It's kind of like greatest common factor. It's that same idea. You have to find the biggest number that works. Square root of 16 is 4. Square root of 3 just stays the square root of 3. So the square root of 48 can be written 4 radical 3. Again, it's kind of like reducing fractions. On this last one, you have a 2 hanging out front. Just hang on to that for now. We'll deal with that in a minute. Let's focus on 90. We want the biggest perfect square that divides into 90, which I believe is 9. The way to check is to see if 10 has any more perfect squares in it, which it does not. 3 does not have any more perfect squares. So you're not necessarily looking for a prime number, you're just looking for a number that has no more perfect squares in it. Once you find it, we take the square root, so that's 3 radical 10. Then the 2 from the beginning multiplies with the 3 that we got from the root. So the 2 and the 3 multiply to get 6, and then radical 10. So anytime you have a number hanging out front, ignore it for a second, and then multiply it back on with your perfect square, whatever that root is, to get 6 radical 10. And you can always check these in the calculator. 2 radical 90, whatever that decimal is, and then 6 radical 10. You want to make sure you get an equivalent decimal. Alright, I encourage you to pause the video, try these 4 on your own, and then play it back and see how you do. Alright, so the square root of 32 should be 16 and 2. That would be 4 radical 2. 72 should be 36 and 2. So 6 radical 2. 200 should be 100 and 2. Square root of 100 is 10. Square root of 2 just stays square root of 2. And 3 radical 24, I'm going to hold off on that 3. 24, I believe the biggest would be 4 and 6. Square root of 4 is 2. Radical 6. The 3 and the 2 will multiply together, and you should get 6 radical 6 when you're done. So there's a whole page of these to practice online and your homework as well. You want to be very, very good at breaking down these radicals. Same idea with perfect cubes. So we have 3 radical 20, I'm sorry, 3 cube root of 24. And so you want to look at your list of perfect cubes this time, not squares. And you want to find your biggest perfect cube that divides into 24, which I believe is 8. And 8 multiplies with 3 to get 24. So you'll do the cubed root of 8 times the cubed root of 3. The cubed root of 8 is 2, and the cubed root of 3 stays in the radical. So it's 2 times the cubed root of 3. And your homework has a little icon at the bottom where you can make a cube root symbol. For 81, again, I want to look at my list, find the number that divides into 81. The biggest one I can find is 27, which multiplies with 3. The cubed root of 27 is 3, and the cubed root of 3 stays in the radical. So it's 3 times the cubed root of 3. 54, the biggest again is 27, but it multiplies with 2 this time. The cubed root of 27 is 3, and the cubed root of 2 stays in the radical. Hopefully you're getting the hang of this. What holds students up is not knowing their multiples, and you've got your calculator to help. You can divide your number by any of your perfect cubes to see if it works. And then we have 4 times the cubed root of 81. So it's the same idea as this one, but there's a 4 hanging out front. 81 we said was 27 and 3. So we'll take the cubed root of that. Cubed root of 27 is 3. Then the cubed root of 3. And then we'll just take that 4 and the 3 and multiply them together to get 12 times the cubed root of 3. Alright, with variables, this can be a little tricky at first. Remember, with variables, we're dividing, not rooting. So it's a very different procedure. We're dividing, not rooting. So for x to the 5th, divided by the root 2, 5 divided by 2, and you can write this out on your scratch paper if you want. 5 divided by 2. 2 goes into 5 twice with 1 left over. So what we're going to have is x squared times radical x. So the remaining power stays in the radical, and however many times it divides is the power on the outside. You can think of this as x to the 4th times x to the 1st. Showing you 2 different ways. This is easier for students usually, but let me show you the other way as well. The square root of x to the 4th is what gives you x squared, and the square root of x stays in the radical. That's how I used to teach it, but this might be easier. 5 divided by 2 is 2 with 1 left over. So whichever way is fine with me. 13, so 13 divided by 2, 2 goes into 13 6 times with 1 left over. Or you can think of this as x to the 12th times x to the 1st. The square root of x to the 12th gives you x to the 6th, and the square root of x stays in the radical. Whichever way you want to think about that. With cube roots, it's the same idea. 3 goes into 10 3 times with 1 left over. And you can put a little 1 for the power if you'd like. You just don't usually see it, but you can put it if it helps. 3 goes into 26 times with, there should be a 3 there, with 2 left over. So what I'm doing, and I'm doing these in my head, but you should be able to do them in your head as well. 2 goes into 13 6 times with 1 left over, so it's x to the 6th and 1 in the radical. 10 divided by 3. 3 goes into 10 3 times with 1 left over, so it's 3 out. And 1 left over. Sorry about that, I had a brain pause. And then the last one, 20 divided by 3. 3 goes into 26 times with 2 left over, so 6 is on the outside and 2 is left over in the radical. So if you're getting the hang of that, go ahead and try these bottom 4. If not, you can watch me again. There's a couple different ways to see it, so just find a way that makes sense to you. 10 into 4, or 4 into 10. 4 goes into 10 twice, with 2 left over. So you'll have, what is wrong here? Sorry. You'll have x squared times the 4th root of x squared. So the 2 on the outside, and then the remainder on the inside. For 31, you'll have, let's see, 4 goes into 31 7 times with 3 left over. So you'll have x to the 7th, and then the 4th root of x to the 3rd. And then the 5th root, 5 goes into 31 6 times with 1 left over, so you'll have x to the 6th, and then you'll have the 5th root of x left over. I know those are kind of hard to see, but you have your variable with your power on the outside, then you have your root, radical, and your leftover on the inside. Last but not least, 48 divided into 5. So 5 goes into 48 9 times with 3 left over. So you'll have x to the 9th with the 5th root of x to the 3rd left over. Your number that's left over in the radical should never be any bigger than your root. It should always be smaller than your root. Because if it's bigger than your root, you can take more out. So that remainder should always be smaller than what you're dividing by. So it looks a little crazy, but it's really just pulling out as many perfect squares or cubes or fourths or fifths, whatever you have, and then whatever's left stays in the radical.